So we now understand how to calculate the electrical power associated with resistors, with voltage sources, with current sources. We've focused on calculating them at the individual circuit element level. But there's something very interesting that happens if you consider the entire circuit as a system, because it turns out that all systems in the real world obey conservation of energy. They have to. Unless you're doing some sort of a nuclear process, there's no way that energy can be created or destroyed. Well, certainly we're not doing any sort of a nuclear process, so energy has to be conserved in our system. This actually turns out to be a very useful way for us to be able to check our work. Here I'm going to consider a moderately straightforward circuit, but it's going to have 3 resistors and a current source. We're going to calculate the power associated with each of those 4 elements. We're going to see that that power has to necessarily balance in the circuit. There are a couple of ways we could demonstrate that it balances. One is we could calculate the power that's being absorbed and verify that it's the same as the power that's being supplied. Or if we consider the power being absorbed for all of the elements, then it would be negative for the ones that are supplying the power, and then it has to add up to 0. Either of those would be appropriate. We're going to first of all calculate the currents and voltages associated with each element. So I'm going to combine the 3 ohm and the 2 ohm resistor in parallel. That's going to give us 2 times 3 is 6, divided by 2 plus 3 is 5. 6 divided by 5 is 1.2 ohms. So using our shortcut for calculating parallel resistance, we're going to get 1.2 ohms. We still carry the 5 ohms from the previous circuit diagram. We still see that V sub S is still the same, V sub 1 is still the same, I sub 1 is still the same, and V sub 2, or we could have written it as V sub 3, they're really equal to each other, are still in the circuit diagram, but I sub 2 and I sub 3 are no longer in the circuit diagram. They simply don't exist because the individual resistors that carried them have been combined into a single resistor. Well, now the circuit is kind of simple enough that we could approach it in one of a couple of ways. We're going to go ahead and calculate the total amount of current and the total amount of power. So here you can see that I1, the current flowing around this entire loop right here, well, it has to be 10 amps because there's a 10 amp source in that loop. So I1 is 10 amps. V1, that's the voltage across the 5 ohm resistor. That's going to be 10 amps times 5 ohms is 50 volts. V2 is the voltage across this resistor, this combined resistor. That's going to be 10 amps times 1.2 ohms, which is 12 volts. The total amount of current, total voltage across the current source by Kirchhoff's voltage law, we get minus Vs plus V1 plus V2, move Vs over to the other side, and we have Vs equals V1 plus V2, which it turns out is 62 volts. So we found the voltage associated with each of the elements, and as it turns out, the current, because they all 3 have the same current as well. Now, what we don't know is we don't know the currents I2 and I3 from the original circuit diagram. We do know the voltage across each of these resistors, though. So that's very helpful for us. So we can calculate the power associated with the current source. I'm going to have to reverse the direction of the current arrow so that it's flowing into the positive terminal. We have 62 volts times negative 10 amps. That gives us negative 620 watts being absorbed or positive 620 watts being supplied. The power through the first resistor is 50 volts times 10 amps, which is 500 watts being absorbed. Now, we could use current division to calculate the other 2 currents, or we could just use the shortcut equations. Since we already know the voltages, let's go ahead and use those shortcut equations. We get 12 squared divided by 3 and 12 squared divided by 2 gives us 48 watts and 72 watts. So there are 4 powers. There's 4 powers associated with this circuit. 620 watts being supplied, 500 watts being absorbed, 48 watts being absorbed, and 72 watts being absorbed. If we add up these 3 numbers that are being absorbed, we get 500 plus 48 plus 72 is 620 watts being absorbed. We find that the amount of power that's being supplied is the same as the amount of power that's being absorbed. If it weren't the case, then this circuit would either be generating power or it would be absorbing a net amount of power. And in either case, that would violate the conservation of energy. If we have any power, if we have a net power other than 0, then energy is not being conserved. So anytime that you're solving a problem like this and you have a few extra minutes, or maybe you're asked to do this, but if you have some extra time, you can always go back and double check your work and see if power is conserved, see if energy is conserved in your particular circuit. So now you have enough information to solve the energy conservation in a circuit example problem, and then you're ready to come to class tomorrow.